All right, let's have a closer look of the detail, of the circuit detail. So as I mentioned, this is a 1/4 circuit, and this is a fully differential amplifier to drive here and there, to the left, to the right, anyway. But the most important issue here is not the circuit itself, but the operation range. Okay, how low the output voltage could be. Maybe you will say, hey, it's delta V, delta V, delta V. Yeah, that is one possibility, but that is only one requirement. But how about the other requirement? If we go to the other route, okay? So you have delta V here, but one VT, one delta V, and the other delta V. What does it mean? For the first route, you only need 3 delta V, right? But for the second route, it requires the minimum should be 1 VT plus 3 delta V. So what is the answer? Because you need to fit both. You need to be larger than 3 delta V, and also need to be larger than VT plus 3 delta V. So definitely, you need to fit 1 VT plus 3 delta V. That's just too much. Okay, 1 VT 5, all right, 500, and 3 delta V maybe 200. So overall, wow. Only for the lower part, you lost 1.1 volt already. That is too much. Okay, so there is another way out. We call it folded cascode. We have many kind of cascode. Traditional cascode, high swing cascode, and right now, I would like to teach you the other more fantastic skill called folded, 折断. Okay, folded cascode, just like this. But later I will explain why we call it folded cascode. Okay, you can see. If you look here again, the original route, 3 delta V. And how about the second route? Because here is PMOS. Okay, so you can guess. Delta V here, right? Okay, but the gate of PMOS can be 1 VT lower instead of higher, right? Because the drain of PMOS can be 1 VT higher. So it means the gate of PMOS can be 1 VT lower than the drain. So here, delta V minus 1 VT. And there, 2 delta V. 2 delta V minus 1 VT. VT usually more than 2 delta V. So it means no constraint at all for such kind of folded cascode. And later I will explain how to make such kind of folded cascode. Okay? But for the new route, you only no constraint at all. Okay, but for the original one, you still have 3 delta V. Okay, so that is the minimum. I think 3 delta V good enough. It's really harder, maybe even impossible to make the minimum lower than 3 delta V. Okay, because 1 mos, 2 mos, 3 moses, so at least 3 delta V. And this is the overall structure: 1/4, 2/4, fully differential to drive both, and counterpart circuit. Okay, and in middle, apply such kind of bias current. And again, wow, you see, folded cascode again. What's that? The major purpose, never mind for high swing cascode or folded cascode, the same. Similarly, to enlarge your output swing. Okay, but why? This is the so-called folded cascode. Okay, later I will show. I will explain. Okay, this is a folded input, and then the major part of your circuit and another high gain stage totally, you still have 2 stages. Oh, don't be cheated. Don't get any kind of misunderstanding. You say, hey, 1 stage, 2 stage, 3 stage. No, because this is the folded input of the case code op-amp. Okay, so those are the first stage, and this is the second. Don't get any kind of misunderstanding. But, oh, sorry. Oh. Allow me to tell you lesson 1. If you see you are NMOS and the op-amp are still NMOS, then you will have such kind of very serious limitation for the minimum voltage, minimum operational voltage, right? So after we change it to be folded case code, you can see it is PMOS. NMOS along with PMOS. That is what we need. Because with PMOS, yeah, the gate can be 1 VT lower than the drain voltage. Congratulations. No limitation with such kind of MPN structure. Okay. But similarly for PMOS, so I need to remind you this. NMOS, this should be P. Folded case code, it should be P. Okay. And similarly, PMOS, this should be N. That's it. Okay? Yeah. But how? Later, I will explain. Sorry for that. I had better modify the orders of the slides. Okay? But anyway, yeah. Again, folded input, PMOS, so NMOS. So this is PMOS. PMOS, this is NMOS. Okay? And those are also PMOS, so had better, should be, the input should be NMOS. That's it. Okay? Yeah. And again, Professor Geiger would like to explain how to make such kind of very high gain op-amp. First of all, you can focus on such kind of very high gain quarter circuit. Yeah, case code and with gain boosting. Okay? Then you can do it by yourself. Easy to test. All right? And how to make it, again, common source. That is the easiest. And then quarter circuit, counterpart circuit, left half, flip to the right, right half, then in the middle. Yeah, you apply such kind of bias current. That's it. And again, where to apply your common mode feedback circuit? Inputs are here, right? So to the other end, here. Okay? And for common mode feedback circuit, again, I will explain in detail later. Yeah, because I mentioned it since last week, but till now, I still don't show you how to design such kind of CMFB circuit. Okay? Yeah, just derive it, estimate it by yourself. Then, we would like to ask you what kind of op-amp we can have with such kind of quarter circuit. And what is this circuit? Again, it is folded case code. It's really upset. Later, I will explain. Okay? Anyway, with such kind of folded case code as a quarter circuit, what is the counterpart circuit? Just flip it, right? Upside down. Then P becomes N, N becomes P. Because you have, this is NMOS, right? And that is PMOS. And this is PMOS, right? And okay, just flip it and swap it. Okay, NMOS become PMOS, PMOS become NMOS, blah blah blah. Okay, you have the counterpart circuit. Then we can have quarter circuit, counterpart circuit, left half, flip to the right half in the middle. That's it. Okay. So what kind of circuit do you have? Oh, that's too complicated to see. All right. So allow me to offer you much better help. But please follow me. Okay. To make the circuit clearer, even more clearer, to have a look at, I mean to see, allow me to use my two hands, yeah, to catch the longest path from VDD all the way to VSS or to the ground. From VDD to the ground, okay? I use my two hands to capture VDD, to pull it up, right? Then shake it. Or I need to shake it because I want the overall circuit from VDD all the way down to the VSS. So I help you to get to capture VDD. Shake it, swipe. Okay, then you will see this. Okay. Maybe you will be curious. Hey, from this to that, what? Okay, please pay attention to again the longest path from VDD to VSS. It passed through VXX, VYY, VAA, and VBB, then to VSS. Hey, bingo! Both way, right? Here and there. But there are still something missed. Okay, for example, where is VZZ? Right? Oh, VZZ actually it attach VDD to the middle of VAA and VBB. Okay, got it? So VZZ attach VDD to the middle of VAA and VBB here and there. Okay? And how about the rest? Who are not taking care of the differential input? Okay? Where are the differential inputs attached to the circuit here? Oh, let's have a look. To the middle of VXX and VYY, right? Here and there are the same, exactly the same differential input. But they will attach to the middle of VX and VYY. Congratulations. Yeah. From the left to the right. That's it. See? But you may be curious what kind of circuit it is. Okay, wait a moment. We still need some kind of little modification. What is the major function here and there? MOSFET with DC bias, it means DC current. Right? So you have DC current here, you have DC current there. Similarly, you have DC current here because that is for PMOS. And VZZ, fixed DC bias, fixed DC bias. Okay? So it means what? DC current flows from here, and input into your VBB. But those two currents, actually, they are redundant. Because they are not involved in the real operation of your operation amplifier, right? Because the input, differential input, is changed into output current, right? And flow from here to the output, blah, 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 blah. For all those DC current, they don't have any kind of impact on such kind of AC operation. So you can see, you have DC current here, DC current here. And also we have DC current, bias current here. And they are summed up to the bottom transistors. It doesn't make any sense because all those two DC current only waste your power. They don't provide any kind of gain. Okay, they are redundant. So we can remove it. But after remove that, it means what? Less current flows through here, right? So you can reduce the W over L of the bottom. That's it. You can save power in the area, why not? Okay? Okay, so after such kind of simplification, yeah, we finally get this. And what is this? Very famous one. Folded cascade op-amp. Again, we prove it. Never mind what kind of op-amp you would like to have. You saw already, or you never see. Never mind. We can create it in such kind of systematic way. What kind of systematic way? Again, 1/4 circuit. Actually, the quarter circuit should be here. Counterpart circuit, left to the right, in the middle, middle here, right? It is folded. It is folded to the other side, okay? In the middle of the symmetry, you can apply the bias current. That's it. And again, where to apply your common mode feedback circuit? Where to apply? Because your input are here attached to there, right? So to the other side here. Okay? Bingo. Yeah. Finally. Oh, I mentioned for quite many times. I will explain later. I will explain later. Finally, this is the moment I will formally explain the operation principle for such kind of folded cascade configuration. Okay. Before my explanation, try to think what is the original cascade structure here, right? See? This is the traditional cascade. But we need to go further. Go to the bottom. What is the function of cascade? Again, cascade transistor needs to be a current buffer, right? The major purpose is to deliver its input current 100% to the output, but increase the output resistance. Okay? But by the way, also decrease the input resistance because you need to absorb 100% of the current into M2, then push to the output. So hopefully, zero input resistance, I mean for M2, and infinite output resistance for M2, blah, blah, blah. So this is the major purpose. Please keep this in mind. Anyway, from the beginning, I explained again and again, right? Input voltage is converted into output current by M1. And then delivered by your current buffer perfectly to output. See? That is two major mechanisms for such kind of cascade circuit. But there is a problem. Because the transconductance transistor, the input transistor, and the cascade transistor, they are of the same type, then the lower voltage of VO will be limited. I mean for NMOS. If they are PMOS, then the upper limit, will have some problem, right? So how to get rid of such kind of limitation? Again, simply because the major cause, the major reason is they are of the same type. So we hope to make them not the same. But how? Okay, by folding. Why we call it folded? Because you can see the current flow all the way down. But right now, it is folded. See? Folded. 折一下. That's it. That is not a straightforward. It doesn't just like here flow from V out to the ground. I mean for PMOS cascade configuration. It is not just like the traditional, the conventional cascade. The current flows down from VO all the way. From M2 to M1 to the ground. No. You can see the current flow is up and down. It is folded. 折过来. Okay, that is the main reason. But again, see, first of all, we need to provide the same mechanism. What is the mechanism? First of all, input transistor, I mean the transconductance transistor, needs to convert the input voltage into output current. Oh, we still make the same thing for M1, right? The input voltage is converted to output current, but how can you promise me the output current will be delivered 100% to VO? You need the help of the other. There is a DC current here. Okay? Please keep this in mind. This is DC. DC means what? It's current in theory. Never be changed. So it is AC opened, right? Bingo, that is what we need. That is all AC opened. It means all the AC voltage converted into AC current. The AC current cannot flow through IQ. According to KCL, it is AC opened. It means zero AC current. So only one possibility. 100% of the AC current, the output current I mean, needs to be flowing this way. And you have no other choice but flow through M2. Okay? So M2 still has the same function as there. See? The input resistance should be very low to absorb, hopefully, 100% of the AC output current, then deliver to the output. Congratulations. And again, if you look back M2 by VO, you can see, you can still see case code because the output resistance here will be multiplied by GM2 and RO2, the same. Okay, the same. Got it? And what is the output resistance here? In parallel, this and that. Bingo. That's it. So if you look back M2, the output resistance is still sky high. Okay, really high. Got it? This is what I am different from all the other teachers. They only show you what is case code. Then what is 40 case code? Even I studied in NTUST, I never got it. Yeah. After I told myself, I was afraid. Some student would raise his hand and ask me, why? Teacher, please tell us why it is called 40. Oh, that is really upset. Okay. Luckily enough, yeah, I warned myself. So I Googled online to get such kind of slide. Actually, this is not prepared by myself, but I help you. Then teach you instead of preach you. 我是老师，不是牧师啊。Okay. Yeah, hopefully, with the help of those slides, you guys in the class get much better understanding than the students in the other class, even in NTUST. Okay, that is I'm really proud of. But I would like to help you even more. So you can see, I help you to highlight different transistors for different function with different color. So for current buffer, yeah, in such kind of, what is the color? Maybe much similar to yellow, okay. And then for folded, to fold the current flow, to stop the AC current flow from here, right? We need help of DC bias, okay? AC opened, DC bias. So I help you to highlight it. The helper, the assistant, 这个助手哈，让你的电流可以转向 IQ in purple. Okay, then we can go downward. Never mind. You can also check this by yourself. Okay, but similarly, this is a PMOS input, MOS input, but to PMOS, and then that is the usual case you learned from how can I say from analog IC design. Okay, Anyhow. Allow me to show you. Who are the helpers? M9 and M10. They behave like IQ. Okay? And who are the current buffers? In yellow. M7 and M8. Okay? And allow me to explain again. If you don't believe in that, okay, allow me to tell you. This is V in. Okay, this is V in, differential input. Then the differential input amplifier help you to convert the differential input voltage into differential output current. Okay, for such kind of AC input, AC output current, they flow. For example, it flows in this node, but M9 tells it, don't come here because I am DC bias. I can only provide DC current. No AC is allowed to be in, right? So all the AC current will be pushed upward, will be folded. Yeah, because from the beginning it's downward. Then it is folded upward through M7 to the upper node. That's it. That is the meaning for folding. Okay? That's it. Hopefully you get all the idea. That is much more important than you analyze the whole circuit after maybe 1 hour or 30 minutes. Finally you get it, but you get nothing. I promise you. Okay? For such kind of derivation, simply focus on 1/4 circuit. Bingo. You will know what is the result. Okay? Okay? Anyway, I hope there is somebody here to help me have some kind of cartoon. If you wouldn't like folded, so what is original circuit? If you don't like folded, you don't need the helpers, the assistants to redirect. That is a very good word, even for software. Right? You don't need somebody to help you redirect the input current to the output. Then you remove it, right? And again, use your 2 hands to shake it. All right? Then this one will flip down. That is original structure. Bingo. Got it? But it is flipped down, flipped downward. So it will become N-type instead of P-type. That's it. Anybody? That is what I can help. You will see how much similarity between telescopic cascode, the traditional cascode op-amp, and folded cascode. They are twins. They are brothers. The only difference again is the helper for current redirection. With such kind of redirection, the downward current needs to become upward or reversely. So it means what? Without it, they are all the same. So here are NMOS, it should be NMOS. But with the help of redirector, original NMOS needs to become PMOS. Got it? Got it? Okay. If you get the good enough concept, then similar issue happens here. Okay? Those two are helpers to redirect the input, the output differential AC current all the way flows through from Q7 and Q8. So they are 7 and 8. They are cascode transistors, and one output here, the other output there. If you hate it, then if you hate folded cascode, you can remove this. Then again, yeah, take it and shake. This will flip upward, right? Then it will become P-type. That's it. That is the P-type telescopic cascode op-amp. That's it. That's it. Wow. And then you can go further. You can say, hey, look, for N-type differential amplifier, it is a tap between Q910 and Q78, right? How about P-type? P-type here, N-type there. What does it mean? You can apply both. Got it? You can overlap this and that. I mean, the main body is still the same. But one, you apply positive, negative input to N-type differential input amplifier and attach the current here to be redirected to the output. And the other P-type differential amplifier attached here, redirect to the output. And what you can get? The gain will be doubled. Not only the gain is doubled, but also you can see for this one, it has some kind of lower limit because you need to have delta V and then 1 VT, 1 delta V. So the minimum VIC is VT plus 2 delta V. Similarly, for this, 1 DT, 1 VDT minus 1 VT minus 2 delta V, right? If you connect both in parallel configurations, you get the rail-to-rail op-amp. It means, again, for N-type, it is functions here. For P-type, it is functions there. But they are connected in parallel. So your input can operate from here all the way to there. Right? Right? The only problem is in the middle. Those differential input are active, are functional. So you get two times, double gain in the middle. Only one gain here with NMOS. Double gain here with both PMOS and NMOS. And finally, only one gain here with PMOS differential input. Okay? But anyway, still better than not. You can fully operate from the ground to the VDD for the input. Okay? Don't forget the limitation for your operation range. Never mind for your input or output. Usually, from analog IC design, they focus very much on output. But sometimes, you still need your input to operate with full range. From the top to the bottom. Then, only one pair means not enough. You need 2 pairs. Okay? Got it? Yeah. To the end of the chapter, you will see such kind of rail-to-rail operation. But I teach you in advance. So the GM, again, how to convert your input, right, into output current. It will becomes 1, 2, 1. In the middle, you will get higher again. If you are upset with such kind of condition, no worries. There is another rail-to-rail op-amp. It is called constant GM. How to smooth the middle one. They hope you don't get double voltage. Okay. When I started in NTUST, suddenly I get one crazy idea. Hey, with some kind of switch. All right. In theory, below it, PMOS. Above it, NMOS. Oh, congratulations. I chatted with my supervisor, Professor Chen Liu Shen. Yeah. He thought, wow, this is a brilliant idea, but with some kind of hysteresis. 你要有迟滞. Okay? It means, in practice, it cannot function in this way. A clear cut in the middle. No. If the voltage here with some kind of noise, your circuit will switch to the left, switch to the right. It will cause a lot of switching noise. Okay, so for switching, you need hysteresis, 迟滞. Okay? It means from here to there, above it, change to the other side. But from the top to the bottom, here, then change to the lower side. That's it. So in the middle, that is the so-called hysteresis. That's it. It can help you to prevent the circuit from oscillation or unstable operation. Okay? Wow, I was very excited. I went for design, but days later, somebody called, his family name is Ismail, Professor blah, 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 Ismail, some kind of Muslim guy, right? He published a paper with exactly the same idea. He's really upset. I thought about it, but Professor Ismail or his students thought even earlier than myself, right? So they published a paper to kill my idea. That is really upset. Maybe if they are interested, they can also apply. Okay. Anyway, anyhow, yeah. Since after, there are a lot of paper focusing on constant GM op-amp. Okay. Yeah. If you are interested, just go for it. But allow me to point out that usually we don't go for such kind of rail-to-rail operation. Okay. So never mention about constant GM or not. We don't care because usually we only operate in this region or at that region with NMOS, this with PMOS, up to your application. So what does it mean? Usually, most of the applications, they don't need rail-to-rail operation, to be honest. Okay? Again, don't try to design the best. You say, hey, I designed a very powerful op-amp to fit all the needs, all the applications. Forget about it. It doesn't make any sense. Okay? Usually, we design something with some kind of defect. 瑕疵. We don't design anything without defect. I mean perfect. Perfect usually means nonsense in practical situation. Okay? That is, I cannot say that is ugly truth, but that is the truth for your own design. Not only on campus, but also in the future. Okay? Yeah, anyway, anyhow. How to apply the biases? Yeah, after you know how to make this configuration faulty or not, how much gain, how high the gain is, I don't care, I don't mind. Anyway, you need a lot of biases. Okay? If without high shrinkage code, you can look back. Oh, you need 1, 2, 3, 4. Okay? You need to pay the price. You need to design 4 bias voltages. But how to make it? How to make it? All right? You can guess. Oh, all right. From MOS side and similar for PMOS side. The minimum should be delta V, 2 delta V. That is what we hope. So again, yeah, from here to there, you need to be, here need to be VT plus 1 delta V, right? And how about this? Because this is delta V, right? So it needs to be VT plus 2 delta V. Similar, 1 VT, 1 delta V, and this one, this one, this one, 1 VT, 2 delta V. To maximize the output stream. But how to make it? Okay, let's go further. Wow. Something similar to here. VT delta V, 1 VT, 2 delta V, right? Right? I don't cheat. But how to make it? For 1 VT, 1 delta V, piece of cake. Everybody is here can make it, right? But how about 1 VT, 2 delta V? I think the simplest should look like this. Again, weeks ago I told you delta V. See? Got it? So how to make 2 delta V? 4L. That's it. And this is the reason why here. Okay? That's it. Yeah, and for the detail, just derive it by yourself. But I need to remind you, according to body effect, here, usually we design longer L. 5 to 6 usually than 4. Okay? That is in practice. All right. So the first cut for your own design, 4 may be good enough. Then according to your edge spice simulation, you need to do such kind of fine tune. And usually between 5 to 6. Maybe you can from the beginning guess 5L or 6L as you like. I don't care. Okay? No. All right, see? This is what I would like to help you even further. Okay, but it's still troublesome. Then allow me to show you this from BS song. Okay, some kind of Chinese or Taiwanese. Anyway, this is what you need to learn. Learn what? Please pay attention to this structure or that structure or even further. Haha. Okay. See? Oh. Bingo. That's it. What does it mean? Many, I mean more than one. Okay. Multiple transistors connected in series instead of in parallel. Okay? Then you can see only the first in saturation. Okay? Only the first in saturation. So here, VT plus delta V. Okay? And how about the others? They will help you provide something similar to delta V, but not exactly. Okay? You can guess according to your intuition. 光靠直觉, right? The more transistors you have, the higher delta V you can get. That's it. Right? So again, don't ask me, teacher, professor, please tell me how many transistors I need to have to fit my application. That is your dirty job, not me, not myself. Okay? As a student, as an employee, the dirty job needs to finish by you instead of your boss. Okay? I only need to talk. Yeah, you need to do. That's it. But I teach you in a proper way, in the best way, hopefully. Let you understand how to get rid of such kind of, from the beginning, maybe somebody doesn't get such kind of, according to, again, delta V, that is my first help. But right now, I would like to help you even further with this, with such kind of structure. Okay? It's much easier. You don't need to, how to compensate this to that. Forget about it. If it is not enough, then you get the second, the third, the first, as you like. Or even you can fine-tune the W over L for this one, for MB1. Okay, that's it, bingo. Do it by yourself. Again, you are supposed, the guys, to finish, to do all the dirty jobs instead of your professors, your leaders in the company. No. Okay, but how to implement all the how to finish all the dirty jobs as soon as possible? Only if you have good idea from your teachers, your supervisors. I hope I can deliver you the most help. Okay, anyway. So the logic thinking is, again, for the first tier, the original one can provide you 1 VT, 1 delta V. Okay? And how about the second tier? We apply this. And fine-tune the W over L, or the number of transistors connected in series. Okay? That's it. Yeah. Then go for your dirty jobs by simulation. Anyway, there's another highlight for you. Fully differential circuit. It means to input to output. Yeah. With such kind of fully differential circuit, the advantage, you have many advantages. But first of all, it can help you to reduce the harmonic distortion. I told you already, right? The even order, the second order, the first order, yeah. In theory, all of them will be cancelled by differential output. Okay, yeah. So it can not. You can say, oh, the harmonics, especially even order harmonics, will be reduced. Okay, or in the other way, you can say the linearity will be enhanced, because I told you we only like this. For the second, the third, the fourth, we hate. Even A0 we hate also, because this is some kind of DC bias. Offset. Okay, yeah, and also with fully differential, you will enhance your PSRR, power supply reject ratio. Okay, why? Because if you go back to see the overall circuit, okay. For example, for some reason, the VDD is increased. All right. Guess what? How about the V out? Usually, it is also increased, push upward. Okay. That is your case. I don't think you have any kind of circuit. If you increase the VDD, then the output will be decreased. Unless you have very special design for compensation. Otherwise, the higher VDD usually means higher output. That's it. Anyhow, the positive output is increased. How about the negative? The same. Okay, the higher VDD, the higher output. Aha! We take the difference. Congratulations. The output voltage difference will be reduced substantially. Okay? So it means what? The outputs right now, the differential output, are more immune, are more insensitive to VDD variation. That's it. That is what we would like to have for PSRR, power supply rejection ratio. Okay, that is the good. But what is the bad? It's fully differential. According to process variation, I told you already, we need the help of common mode feedback circuit. Otherwise, according to process variation, the output common mode voltage won't stay here. 50% to be higher, 50% to be lower. Then the output swing will be reduced substantially. Okay? How to push the output common mode voltage back to the middle? That is the major job for CMFV. Okay? All right. Let's have a short break. Oh, okay. Oh, wait a moment. Allow me to explain the concept then for detail after the break. Okay? So you can see, again, the input here, attached there, so to the other side. Okay? That is the easiest way to check where to apply your common mode feedback circuit. And then, the concept is, if the common mode voltage is higher, then you need to push it back. But how? All right. You need to increase the bias for the transistor to the other side. I mean, yeah, at the other side of the input. Okay? Why? All right. Yeah. I am talking about the concept for detail later after the break. If you increase the output of common mode feedback circuit, M1 and M2 will get higher VGS. Higher VGS means what? lower resistance, more conductance, right? So, because the resistance here is reduced, the voltage here, and on top of it, the voltage there will also be reduced. That's it. Bingo. So, what I'm talking about, please keep this in mind before the break. The higher output common mode voltage, the higher output for your common mode feedback circuit. That's it. Okay. If you see the VOC is lower, it's too small, then you need to also reduce the output of your CMFB. It means M11, M12, M11, M12, the VGS become much smaller. It has a lot of output resistance, right? And the current actually flows control, the bias controlled by this one, by the current redirector, I told you already. Okay, they control the bias. So the same bias provided by M6 and M5 flows through much larger resistance. It means the voltage here will be increased. Yeah, at the same time, because V out on top of this and that, VOC will also be pushed higher. That is what we need. Okay, that's it. So the input, the output of CMFB needs to be synchronized with the input. That's it. The higher VOC, the higher CMFB output. The lower VOC, the lower CMFB output. That's it. That is the key idea. But after you get the correct idea, after the break, I will tell you how to realize it. Because CMFB is usually the bottleneck for new designers. Why? Because you never learn it from your microelectronics. Okay? And later, right now I explained the idea already, and later I will show you. Piece of cake. It's really easy. After you get the correct understanding, it's really easy to understand the operation principle of any kind of CMFB. Okay, I will explain some to you, not all to you. Okay, because we don't have time. All right, let's have a short break right now.